Whoa, hello! Didn't see you there. Oh, well, this is awkward. So, do you like stuff? Are you interested in anything? Because I got this great thing coming up. I'm so ready to talk about this great thing. You ready? You ready for it? Yeah? Yeah, you excited? You excited as I am? Because I'm gonna talk to you about mortality graduation. What is mortality graduation, you ask? Well, that's a very good question, my dear. But before I tell you, I must discuss the context. Let me just walk over here and show you something real quick. This is a graph, and if we look at it, it is extremely ragged. And that is because all the rates from any mortality investigation will only be crude rates, and these crude rates on the mortality curve will exhibit raggedness. Well, what's wrong with that, you say? Well, the aim of graduation is to simply remove random sampling errors that may be present in graphs that are too ragged. So in essence, graduation is a refinement or a smoothing process. We use the adjacent age mortality rates to improve our mortality estimate overall. The smoother the graph, the easier it is to estimate. And we really like these smooth rates, they're really easy to work with. And with incredulous speed, I'm going to draw on this blackboard a graph which shows the relationship between mortality rate and age. Bam! And done. The dots represent mortality rates, while the curve we fit to the data so that it is a smooth curve. So in summary, the aims of graduation are to produce smooth rates, to help remove sampling errors, and improve rates by using information from adjacent ages. Now that we've established that graduation is important, there are certain criteria into what we want from graduation. Firstly, we would like adherence to data, we would like the curve to be very smooth, and we would like the curve to show suitability for the purpose at hand. Now that we have established how important graduation is, there are certain criteria into what we want. Firstly, we would like adherence to data. We would like the curve to be smooth, and we would like the curve to be designed in such a way that there is some suitability behind how it's used. If you remember this graph, this is a graph showing mortality over age. But here, in this instance, this curve is far too overgraduated. And here is an example of a graph that's undergraduated. However, there is always an offset, a balance, if you will, between smoothness and adherence to data. You cannot have something that is perfectly curved, nor can you have something that adheres perfectly to data. So the real important issue is to find the balance, the perfect balance. How do we do this? Well, very simply, we just use a number of tests. Our aim is testing for adherence to data, and this test relies on the assumption that the true parameters of the underlying probability model are the graduated rates. Our null hypothesis is therefore the true underlying mortality rates at each age x for the experience are the graduated rates. So in essence, we are testing Qx, which is the mortality rate, and mu x plus half, which is the force of mortality across that age. We are testing if these parameters are equal to the true parameters of the underlying model of probability. So now we've talked about adherence to data and smoothness, let us now discuss suitability. If we are doing pension or an annuity work, it is absolutely imperative that we do not overestimate mortality. We would like to calculate third differences, which measures the change in curvature. For the graduated rates to be considered smooth, we want the third differences to be small in magnitude compared to the graduated rates themselves, and we want them to progress regularly with age. And there are 6 statistical tests that we conduct to see whether the graduated rates, are equal to the true parameters of the underlying probability model. The first of these is the chi-square test. This test tests overall goodness of fit. It has only one parameter, which is the degrees of freedom. The second of these is the standardized deviation test. This is used to detect a number of excessively large deviations. We investigate the distribution of the values of the standardized deviations. The science test. The science test is a simple test for overall bias, whether we over or underestimated our data. If there is no bias, we expect equal numbers of positive and negative standard deviations, and this will be a two-sided test as we are finding out if it is either above or below the data. Test number 4, the cumulative deviation test. This is a test for overall goodness of fit. Poor fits may be due to homogeneity, so this testing method could even detect homogeneity. Otherwise known as the grouping of signs test, this is a one-sided test since we are only concerned about a low number of groups, so we definitely do not use this test on undergraduation. Last but not least, we have the serial correlations test. Our null hypothesis should be that sequences of ZX's should not be correlated, that is, sequences of lag 1 and length n-1. So that, in a nutshell, is exactly what mortality graduation is. See how fascinating the life of an actuary can be? Thanks for watching, and I'll see you again next time. Oops, got a call. Looks like some of my classmates need me to help finish off an assignment. Well, I've really got to go. Bye-bye.